Hello and welcome back to Calculus2, section 7.2 on exponential models, part 2. So we're going to talk about decay this time. Last time we talked about exponential growth and we used population as an example. We define the exponential function over there, which is exponential model, and then we say we can use it as a population, we can use it as a decay of mass, and a whole bunch of different cases, whether you have k positive or negative. We used the population, we did some calculations, and we ended with computing the limit first to show that the population model is not good for long term because gave us infinite population, which is not feasible to have on a finite planet size. And then change in population you can calculate by working out the derivative of the model and then plugging in the year you would be interested in to find how many people are added to the population in that particular year. So that was our last class. Today we are going to take a look at decay model, right? And take a look what's happening with the loss of mass. Now, every kind of decay is modeled with the same formula, with a negative k, and we define a parameter called half-life, which is, on the side of being a very popular video game, it is a time in which the mass of the object decays to half of its original value. So we are going to define that, and we're going to compute or see the formula for half-life. And then you can use half-life that's stored in charts and tables, and you can use half-life to say, to argue on garbage disposal, and how long will it take for a garbage bag to decay to 90% of its original mass, or something from plastic, or even the organic materials as well. I mean, everything decays. But then also we are talking about a radioactive decay, and then in general garbage decay, because we need to deal with garbage on the global level, because we do as a species generate a lot of garbage. Again, planet doesn't care, right? Because all of that garbage came from the planet. We just put in a different order, those molecules, right? Because you have to understand that 100% of stuff, which includes the garbage that we produce on this planet, was everything part of the planet. So all of those stories save the planet and it's not save the planet, it's just save our environment for us to live. The garbage, the planet can't care less if there is a plastic bag floating around, because all of that plastic was taken from Earth resources and rearranged into a plastic bag. There's a famous joke which says, why do we exist? Plastic. Planet couldn't figure out how to make plastic, so he needed us, right? And that's it. That's the purpose of human, to just make plastic, which is oil, right, from the ground. So let's talk about half-life. Let's first write decay, and then the first is half-life. Lambda is a Greek letter, right? Lambda is the symbol for half-life, just like in a video game. And half-life is time in which object loses half of its original mass. Actually, I don't want to use the word original. I want to use the word initial. Initial mass. When you are taking my pre-calculus class, just like when you are taking my calculus and differential equations and so on, there's a project which is due the day of the final exam. So one of the projects for my pre-calculus class, because this lecture is technically pre-calculus 1, chapter 3, they had to figure out how long will it take for this marker, right? This is a regular Expo marker made out of plastic. How long will it take for this marker to decay to half of its weight? They went to the lab. They measured that this was 16.2 grams, if I remember, on those scales you have in a chemistry lab, right? Then they were doing the research of what type of plastic is used to make this, what is the half-life of plastic, of that particular plastic, and then use the information they collected, right, through the formulas that we have to calculate that it was going to take about 10,000 years for this marker to lose half of its weight. And then it's going to take another 10,000 years to lose the half of the half, which means a quarter remains, another 10,000 to take it down to an eighth, and so on. So the decay, right, in our human perspective, is a very long process. Again, save the planet, nya, nya, nya. No, because the planet has been around for 5 billion years, so if the planet has to wait for this to decay 10,000 years to its half, nothing, right? So yeah, there you go. All right. Lambda is time. If I have y equals a e to the kt, where k is less than 0 to get us decay, we are going to say m is equal to m of t, which is the mass at any time, and capital M is initial mass. So I can write the formula m at any time is initial mass E, and then if you want to put negative kt, go ahead. If you want to put kt, you have to write k less than 0. Since I'm lazy, negative kt. So it's clear, right, that it's a decay model. Now I am going to calculate the formula for half-life. Half-life is lambda equal, so t equals lambda, or lambda equals t, whatever. So that's what, t equals lambda is better. T equals lambda. So t equals lambda. So now, if I am to, so when you have half-life, your t is equal to lambda, and your mass is half of the initial mass, right? Because that's what the half-life definition is. So the mass of this is a lowercase m, and then there is a capital M. Lowercase m is the mass at any time, and the mass at any time, right, is going to be half of original mass at some point. So now you plug those into the model. You have m over 2 equals m e to the negative k lambda, no t. Now you're plugging in lambda, because when you use the lambda time in the formula, then you are guaranteed to have that the mass is half of original mass. At this point, initial mass cancels, and you have 1/2 equals, leave some space, e to the negative k lambda. You want to calculate lambda, so you hit this with ln on both sides, and you have negative k lambda is equal to ln of 1/2. Lambda is equal to ln of 1/2 divided by negative k. So this is the formula which connects the time lambda to the constant of decay, and we can use it to figure things out. Now, generally, lambda is stuffed in the tables, so you guys can just read the lambda, and the half-life is not only given for radioactive elements. Half-lives are given for technically anything, and more. What is it more? Half-life of medication to metabolize in the bloodstream. We'll briefly talk about that as well. But I want to, go this lecture a little bit different way. The first problem we are going to do is, you ever heard of doormat? Doormat. People are already Googling. How about teeth whitening? Anyone into teeth whitening? Do you buy the tooth whitening toothpaste? Yeah, right. Because we want that nice shine, right? And that beautiful smile. Awesome. So doormat is the first ever tooth whitening toothpaste from 1942 and 1943. I pulled it up. Look at that. There it is. That's the actual tube, right? And there's that woman smiling over there, clearly glowing, right? It's in German, but you can read this word over here. Oh, okay. So 1942, it's around there, and they figured out that if you use the isotope of thorium, thorium-229, and brush together with the paste, your teeth have the whitest glow you can possibly imagine. So they packed it into tubes, made all of these, as you can see, propaganda, right? All of those ads and commercials, and sold it to the people who brushed, got their teeth very nice, clean, and bright white, and then they all just died. So, from various bad conditions. What is thorium-229? Well, there it is. Thorium-229, radioactive isotope with half-life of 7,340 years. So it's a radioactive element, and as you can see over there, it's generated by the decay of uranium-233. So potent, right? And then it's packed in a toothpaste and sold, right? So let's take a look at the problem and see, after these people have been dead, 80 years now? So let's see what is the amount of thorium on their teeth 80 years later, right? So let's ask ourselves, we have a doormat toothpaste which has thorium-229, I hope. Doormat contains thorium-229 with half-life of 7,340 years. what is the percent of remaining, or what is the percent of what? I have to reset my English. Back to push the button. What percent of thorium, what percent of thorium-229 is still present 80 years later on the teeth of those people who use the toothpaste in 40s. So it's been roughly 80 years. Well, we know our decay model. It's mass equals initial mass. This is how much thorium has been put on the teeth. E to the negative KT, or positive KT, whatever. If you put the negative K, it will be positive. If you put positive K, then it will be a negative number. So it has to end up negative anyway. And we know that the lambda is given to us as 7,340. So we start the problem by half of initial mass that was in the paste equals ME to the negative 7340 K. The mass will cancel out, and we get 1/2 equals, leave some space, E to the negative 7340 K. ln both sides, and what you get is, now you use the abacus to figure out ln of 0.5. You have the button for that. We talked about it last class. So here's the button. ln 0.5 will give us negative 0.6931 equals to negative 7340 K. So when you divide this by 7340, remember you have to use 4 significant figures. You will get that K is equal to 0.00009443. Right? So I didn't use 4 decimals, because 4 decimals is just 0.0001, right? I used 4 significant figures. Those zeros leading up to 9 are not significant in sciences. If you took physics and chemistry, you know exactly what I'm talking about. If you have never taken physics and chemistry, you are learning it now. Significant digits, zeros are not significant. 9 is the significant digit, right? It's the stuff that would end up in a scientific notation. So use the 4 significant digits. So we are cutting off and throwing in the garbage all of those zeros, and then we know that we need to keep 4 of these. Now you can't throw them in the garbage, you need them in the constants, right? So it's there. All right, now we have our mathematical model. M equals M E to the negative 0.00004, no, 9443 T. This over here is your thorium model. And now you want to know how many, what percent is left. What percent of what? Well, what percent of the original amount brushed on their teeth, because the thorium has been decaying along with the corpses, obviously. So the percent P times original mass is equal to ME negative 0.0000943 times 80 years, right? So this is 80 years later. M will drop again on both sides, and we are going to have P equals E to the negative 0.0000943, no coughing, times 80. So now we go E caret, open parenthesis, point, 1, 2, 3, 4 zeros, 9443 times 80, close parenthesis, and we get no bueno. What did I do? I got 1 point and I don't like it. Oh, I didn't put the negative. So, clear everything. E caret, open parenthesis, negative point, 1, 2, 3, 4, 9443 times 80, close the parenthesis, and there it is. P equals 0.9925. That translates into 99.25%. So after 80 years of decay, how much thorium is still on their teeth? Everything. Everything is still there. You see that? These are the most beautiful courses, right? Yeah. We don't know until it's funny, someone in 300 years laughs. It's like, yeah, they used to live only about 100 years because they used to drink milk, right? Look at us, we don't drink milk, we're going to live like turtles. No, turtle is short-lived, right? Tortoise is the one that lived 250 years. Tortoise, yeah. Cool. We have this, right? Quick question. Dosage for medication. Is that a suggested thing or we should follow it? Probably follow it, right? Right? Metabolizing drug in a body is exponential decay problem. And the drug is not metabolized linearly. So, when you take a dose of medication and then you wait appropriate amount of time and then you take the next dose, which was the same as the first dose, the amount of the drug in your system is increased. Every next dose of the same level always increases the amount of drug in the system, which makes perfect sense for easy dependencies. Right? And there is an opioid crisis, we know that. But let's take a look at how long do you wait before you take next dose of Advil? 4 hours. Like that. Why? Right? The bottle said so, right? The doctor said so. And how do they know? Right? So now, These are some things that, if you care, you can do. Do we all know Wolfram Alpha? Good. So, other than cheating on your homework integrals, you can type Advil. It tells you that the real name is ibuprofen, gives you all of these chemical and chicken fences and things so you can cook it at home if you need to, right? Tells you how it interacts with other drugs, and wait for it, biological half-life, 1.9 hours, right? Okay. So, what happens? I know that the dose is usually 200, 250, or 500, but those numbers are annoying to compute. So what I want to compute is what if the original dose is somehow 400, because I'm lazy, right? So 400 milligrams, right? Those are the. So let's just see some calculation without calculus and pre-calculus or anything like that. You take 400, and then you wait. Half-life is 2 hours, right? So wait 2 hours, because half-life is 1.9 called 2. How much is left in the body? 200 left. And then you wait another 2 hours. How much is left? 100. Yeah. Why is it 100? Because half-life, which is the time of 2 hours, cuts the original amount in half. So you don't get to subtract 200 every time. You subtract the half of the amount that is left. So if you took 400, you waited 2 hours is 200, you wait another 2 hours, it is 100. But how much time passed from 400 to 100? And then what do? Because you said so, you pop another one, right? There we go. Boom. And how much do you have? Okay, cool. Wait 2 hours. What do you got? Oh, 250. Wait another 2 hours. What you got? 125, right? 125. That's another 2 hours. Hold on. 2 hours, 2 hours. Boom. Are we ready for plus another 400? So, next one is 525. So you went from 400 to 125. From 400 to 500 to 525, right? Do you see that the dose that it's present with every dose you take goes up every time? So for those highly addictive medications, what they have? Weaning off. It's not just, boom, cut and out. They have, instead of taking a pill, take a half a pill, take a quarter of a pill, right? Or they pre-package, 400, 400, 400, 200, 150, right? Few days to get off the medication. Right? Right. What kind of... Now, if this is metabolizing, and let's say you never take another dose. You took 400, and it's metabolizing at the half-life of 2 hours. At what time is everything gone? Never. Why? It's exponential decay function. Does it hit x-axis? Yeah, at infinity. I don't think you're going to last that long, right? So exponential model is, here is your 400 dose as time goes to infinity. With a sophisticated enough method, maybe we don't have it, I should pick up every single thing you ever took and every single thing your mother took, right, while you were in the tomb. Right? Oh, not tomb, womb. That's the word. Why are they so close? They shouldn't be rhyme. They shouldn't rhyme at all. Anyway, so now we see this, and if I am to ask, let's say on a test I come up with aspirin, I come up with something else, right? Same calculation you have here, right? It's the same calculation. You go and you say, all right, this is the dose, and the dose is your capital M, right? And then you have your half-life given in a problem. That's going to be time, and those two will be enough for you to calculate K. K for every drug will be different, but then also medication has different effect on different people, right? Some people take a drug, they get better. The other ones get drug, feel better, and then constantly bleed from the left eye for the rest of life, right? So side effects. So you have to understand that, you know, that K is way more complicated than, right, because we're all different. So there's a lot of things that go into there, but you see that there is a science behind it. These things are calculated. No one guessed these things and said, all right, just print that on the bottle, let's see what happens for like 2-3 years, and then, you know, we'll adjust it later. So there is a whole market of computing these things for pharmaceuticals and so on, and they are not really forgiving if you forget a minus, or you just, can I get a partial credit because, right? Because when you mess up on those kind of things, a lot of people die, right? So these calculations are checked and rechecked and really, you know, worked out down to the T to make sure that everything is correct so they can actually sell the drug. And it's still not working in some cases properly, but such is life. What can I compute again? Well, I can take the integral of the model to compute the accumulation, right, which will detect every extra along the way. So if you're taking something for like 3 years, you can figure out on average how much stuff you entered in the system, right? Because the integral has a number to a number, and those numbers are months or years. So it will add all of the, right? We know that the integral is a sum, so it adds all of those differences to create one large pile of stuff, where the change, which is the derivative, tells you in one instant of time, whether it's one dose or, you know, over some period of time, tells you the change, which will be the single incremental increase at the time. One more thing that I wanted to do with the growth, which I forgot, is a very interesting problem, which says, how long do you have to wait to double your investment at 4% or 3%? Let's do 3%. So another exponential problem. How long do we have to wait? Now, obviously, it's in years. It's an investment problem. How long do we have to wait to double? You can go with triple, quadruple, I don't care. To double investment at 3%. So we know our growth equation, which is that the amount is equal to principal, which is the money either borrowed or the money you lend, e to the kt, rt, r for a rate. So P is the amount invested. A will be a payout after a couple of years. If you are borrowing money, then P is the amount of money you took as a loan, and A is the amount of money you have to repay after interest is added. It's the same formula. You are on one side or on the other side of it, right? Because it's the same formula. You go to the bank to borrow the money to buy the car. The bank lends you that same money. You pay interest, they collect interest. It's the same money back and forth, right? The question is, which one are you, right? Is it this way or that way, right? So that's why it's the same equation. You just have to be a little bit careful what side you're on. Every time you put money into savings, that money, very slowly, grows a little bit, right? Because generally banks and savings accounts have some little percent. Now, why do they have that? Why do they have the percent? To encourage you to put the money into savings, because when you put the money into savings, they use that money to lend to people. They make percent, and out of the big percent they make, they give you a little bit as the incentive to put more money. So technically, bank makes money with your money, because if everyone in this classroom puts in $100 into savings, bank has $3,000. And then one person is going to go and say, I need $3,000 to buy the new computer, or to pay for a class, or to buy a car, right? So now that person is going to collect $3,000 as a loan. The bank is going to charge this one person interest, and then everyone is going to get a little speck of that money, but the bank is keeping, right? So that's how they make money, so they can have salaries and, right, feed their kids and stuff like that. So interest is the service, right? Because if you are not able to borrow money anywhere, then you can't buy a car if you don't have a duffel bag with cash, right? So interest is service. Interest is not something that the bank is stealing from you. It's simply you borrow the money because you don't have money, and for that service you have to pay. Just like you pay service when you go to a mechanic, you pay to rent a room in a hotel. Well, if you are renting money from someone, you pay for that service, and that service is not called service, it's called interest. But then people, right? So you have school loans, government interest, 2%, 4%, private loans for school, 5, 10, right? So you figure out which loan you want because the interest is given. Is everyone swiping their credit card for Starbucks? Yeah. Why not, right? It's not your money. Yeah, it's not. It's actually, every time you swipe a credit card, you borrow the money from the bank at probably 30%, right? Interest. So your coffee is no longer $3, now it's like 3,000. So good luck. That's a good margin. Only in my bank, okay? If you want to open credit card with me, let me know. You'll be paying off the bagel and the coffee in the morning forever. Anyway, that was one of the best. It's like, oh, you know nothing about math? You don't want to learn anything about math? Can I be your accountant? Because it's so helpful, right? Anyway, so if I want to double my investment, what should I put here? 2p, right? So you put, right, you are investing into something and you want to double it. E to the 0.03 p. Do we all see that the p drops on both sides? Yeah, right? So we just have 2 equals, leave some space, e 0.03 t. Hit both sides with ln. And now use the abacus to figure out the values. ln of 2, 0.6931 equals to 0.03 t. Divide by 0.03 and get t equals 23.1049. So 23 years. It will take 23 years to double your investment. Great. So let me ask you a question. Who makes money makes money. We heard that, right? Did we? Do we understand it now? Let me ask you this. If you invest $1 and wait 23 years, how much do you have in the account after 23 years? $2. If you put $1 million in the account and wait 23 years, how much do you have? $2 million. Do you understand that? Yeah. So if you are 20 years old and you somehow manage to put $1,000 in the account, how much do you have when you are 43? Yeah, 2,000, right? Now, if you're 55 and you put $1,000 in the account, what do you have by the time you're maybe dead? You have same $2,000, right? Which is time to save and not waste on Starbucks and stupid things that you don't need. Especially you don't need a new cell phone every year. You don't need a lot of other stuff, especially not when you're working for $12 an hour, not in your field, right? And you shouldn't be, because you can tutor math for at least 30, 40 an hour, but you just don't want to because you like your $11 better at the schedule that someone else gives you. Yeah, you're insane. But I can't help you. It takes one stupid toaster. That's all it is. Go shovel fractions at $20 an hour. I mean, come on. It's all sitting in Calc2, trying to figure out what's what. Anyway, that's our lecture, right? That's exponential functions. Every one of these formulas can be integrated, can be differentiated depending on what do we want to see, right? You can take the limit over here and see that if you wait infinitely long, you will have infinite amount of money invested, right? And it's kind of scary to think that Bill Gates would have like 85 billion times more infinity than you at that point, right? Let's take a short break. When we come back, hyperbolic functions.